Welcome to the Explainer. Today, we're taking an absolutely epic journey straight to the edge of a black hole to test the very limits of physics. We are literally smashing together two massive, totally different worlds. On one hand, we've got the ultra-precise, delicate realm of quantum mechanics, and on the other, the heavy, mind-bending gravity of general relativity. Okay, let's dive into this because it's honestly one of the most fascinating questions in modern physics. If you were to drop a highly precise quantum device right near a black hole, do the rules of physics fundamentally break down? For decades, physicists have wrestled with this intense friction between quantum mechanics, the stuff that governs the microscopic world, and general relativity, which dictates massive gravitational fields. Well, today, we're going to look at a brilliant thought experiment that finally gives us a clear answer to this mystery. So, Section 1, a quantum thought experiment. To tackle this, we're looking at a really fascinating recent study published in the Journal of High Energy Physics by researchers Pantech and Övgün. Basically, they decided to mathematically test what happens to a quantum circuit in the curved spacetime just outside a black hole. Which brings us to Section 2, the Josephson Junction. Before we go dropping anything near a black hole, we kind of need to know exactly what kind of hardware we're working with, right? For this thought experiment, we're using something called a Josephson Junction. Essentially, it's two superconductors separated by a microscopic, ultra-thin barrier. Without getting totally bogged down in the jargon, what you really just need to know is that this device carries current through the collective quantum phase of paired electrons. So if you apply a constant voltage to it, it actually turns that voltage into a highly precise quantum oscillation. You can think of it as a macroscopic, real-world expression of delicate quantum coherence. Now, let's see how this builds into an even more powerful tool. If you take two of these Josephson junctions and place them together in a superconducting loop, you get what physicists call a SQUID. And yeah, that stands for Superconducting Quantum Interference Device. This setup creates an ultra-sensitive interferometer. It's a tool that is just hypersensitive to even the most minuscule changes in quantum phase and magnetic flux. It's basically the ultimate precision quantum measuring stick. Moving right along to Section 3. A tale of two clocks. So now that we have our ultimate measuring stick, what actually happens when we introduce it to the intense, curved space-time of a black hole? To really understand the friction here, we have to talk about how gravity messes with time itself. Our key metric for this is the gravitational redshift factor, which we represent with the Greek letter alpha. When you're floating safely far away from a black hole, alpha is basically just 1. But as you get closer and closer to the event horizon, alpha approaches 0. What this means in plain terms is that a clock situated deeper in a gravitational field runs much, much slower compared to a clock further away. Time is literally relative to where you're standing. Now, what's really interesting about this slide is how it frames two completely different perspectives. We've got a local scientist hovering right next to the junction near the black hole. They're using their own local proper time, and to them, the standard Josephson relations are working perfectly. No issues at all. But then we have a distant observer sitting safely far away from the black hole. Because of that gravitational redshift factor we just talked about, this distant observer is using a completely different clock. They're going to see redshifted voltages and frequencies. The two observers fundamentally disagree on what they're measuring, simply because time itself is ticking at different rates for each of them. Let's look at the math strictly from that distant observer's perspective for a second. As the device gets closer to the black hole, the readings they get drop significantly. The critical current reading contains 1 power of alpha. This means as alpha shrinks near the black hole, the apparent current shrinks right along with it. But then look at the measured power. It contains 2 powers of alpha, meaning it's multiplied by alpha squared. So as the junction gets deeper into that heavy gravitational field, the distant observer sees the current decreasing, sure, but they see the power decreasing even faster. All right, Section 4, readings, not rules. This brings us to the absolute most exciting part of this explainer, the massive plot twist and the researchers' calculations. You might think that dropping a vertical squid near a black hole would totally break the quantum interference pattern. Like maybe it would shove the whole thing sideways because the top and bottom of the device are at slightly different gravitational potentials. But the calculations show that intense gravity doesn't break the local quantum rules at all. Yes, the overall amplitude is rescaled, and the shape of the envelope gets a minor deformation. But crucially, the lobe centers, the anchor points of the interference pattern, remain exactly at their usual magnetic flux values to first order. The physics holds firm. No broken rules here. So, the crucial point is this. When we introduce radio frequency driving to the device, we do see some apparent translations in the interference lobes from afar. But this isn't because the quantum pattern is actually sliding or breaking down. Not at all. It's entirely due to the phase accumulated while the signals travel through curved spacetime. It's a phenomenon known as the Shapiro time delay, where gravity literally slows the signal's journey. Think of it like a massive traffic jam for light. This delay creates the illusion of a shift for the distant observer, but the core mechanics are untouched.
The researchers summed this all up with a really brilliant analogy. They described their mathematical framework as a dictionary. On one side of the dictionary, you have the local microphysics, which remain perfectly intact. On the other side, you have the distant bookkeeping, the redshifted observations from afar. Having this dictionary ensures that we don't mistakenly assume a quantum superconducting state has broken down, when really it's just the translation of measurements across a severe gravitational gradient. Near a black hole, the quantum rules don't change. Only the readings change.
And finally, Section 5, why this distinction matters. Let's bring this incredible thought experiment safely back down to Earth. Why do we actually care about a hypothetical squid hovering over a black hole? And this brilliantly illustrates the scale of what we're dealing with. On our own planet, the differential effect of gravity is incredibly tiny. If you separate 2 points vertically by just 1 single meter, the fractional gravitational redshift is only about 1 part in 10 to the 16th power. That's roughly 1 in 10 quadrillion. It is a microscopic difference, completely buried under the ordinary noise of our current laboratory Josephson devices. However, just because it's small on Earth right now doesn't mean it's irrelevant. Actually, it's quite the opposite. Drawing this exact boundary between actual quantum dynamics and the effects of gravitational redshift is absolutely vital for the future of highly precise near-term Earth science. As our technology in precision metrology gets sharper and sharper, and as we build complex analog systems meant to reproduce strong field kinematics right here on Earth, we need that mathematical dictionary. We absolutely have to know exactly how to separate true quantum behavior from the subtle tricks that our planet's gravity plays on our clocks and energy standards. By placing our most delicate quantum devices into the most extreme gravitational environments, even if it's just in a thought experiment for now, we've proven that the rules of the quantum world stand their ground. Gravity might warp the message, for sure, but it doesn't break the machine. So if these rules hold true even at the edge of a black hole, it leaves us with one incredibly thrilling question. What other cosmic mysteries can quantum metrology unlock next?